So today we finish our unit on wastewater treatment. We've talked about the liquid stream, which includes preliminary treatment, primary treatment, secondary treatment, tertiary treatment, disinfection. But during preliminary treatment, primary treatment, and secondary treatment, in some cases tertiary as well, you have a separation of the liquid stream and the solid stream. Right at the bottom of the primary tanks, you have what is called primary sludge that settles out and has to be dealt with. In the secondary tanks, you have your secondary clarifiers, and in the secondary sludge, you have some of that gets returned back to the process as return activated sludge. And there's another portion of it called waste activated sludge, which has to be wasted. So secondary sludge that needs to be processed. So this is just a brief lecture on wastewater solids handling. The sludge coming from those clarifiers is not an easy thing to deal with. It contains an unpleasant odor, it has pathogens, and it has a lot of water in it. So it's very heavy. So if you're going to move it around anywhere, it takes a lot of energy to do that. So the first two problems are dealt with in various ways, and those are referred to stabilization process, referred to as stabilization processes. And there's three primary methods. One is called lime stabilization, and I'm not going to talk very much about that because essentially what's done there is you just pile the biosolids up and add a bunch of lime, which is calcium hydroxide. And that lime has various ways of killing or deactivating the pathogens as well as keeping the odor down. Very simple process. Nowadays, more modern processes typically either use aerobic or anaerobic digestion. I would say anaerobic digestion is the more popular of the two in most treatment facilities, but aerobic digestion is still quite common and around. And these are processes in which microbes do additional processing or consuming of some of the problematic parts of the biosolids. In aerobic digestion, aeration is required, just as in the aeration basins. But in this case, the organisms themselves begin to kind of consume each other. Instead of consuming BOD, organic material that's coming in the wastewater, that's all gone, and all that's left is themselves. And so you kind of manipulate the process in order to make sure they can consume each other. This is good for pathogen destruction. Odors can still be a problem in these processes, but they're fairly easy to maintain. They do have an energy input in the form of the aeration, but the main advantage of aerobic digestion is that it's an easy process to maintain. As opposed to anaerobic digestion, which is probably the most popular, where in this process there's very little to no energy input. There may be a little bit of additional preheating depending on the environment, but out of this process you generate quite a bit of energy in the form of methane, and that methane can be harvested and combusted to create electricity, which can then be fed back into the process. And a lot of treatment facilities are becoming completely energy independent because there's enough energy that they can create through anaerobic digestion to power all the processes in the plant. In anaerobic digestion, no aeration is required, so no energy for pumping air. Very good pathogen destruction, but it's a very difficult process to maintain and operate because there are multiple organism groups all doing different things. And some of the organism groups create waste products that are toxic to other organism groups that also need to be part of the process. So it's essentially a large food chain of microbes where one does a certain process and creates certain products that another needs, but some of the waste products of these different organism groups are not good for the others. So especially in terms of pH, but also temperature, there can be a problem. So one of the organism groups creates a lot of byproducts that are acidic and would serve to draw the pH down, but there's other organism groups that are very sensitive to that low pH. And so it's very difficult to tweak and tune in order to get it to be working really well. But when it is working really well, it does everything you want it to do in a very good way, and in fact can generate electricity. So those are the three main processes. So that handles these first two, unpleasant odors and pathogens. And from anaerobic digestion, what comes out is a relatively stable and non-objectionable material. It's similar to compost or soil. It does have some smell, but not to the same degree that you would have in aerobic digestion, and certainly way less than what it had originally. Now, excess water. So the third problem is that it's heavy. So excess water can be dealt with through a process called dewatering. And really, it's a combination of thickening and dewatering, which are two separate processes that use some similar physics, essentially. And the three main processes for dewatering are drying beds, which is just, hey, I'm going to put all the biosolids out in like on a big pavement slab and let the sun dry it and the wind. Belt filter presses, which are belts that are pressing against each other and forcing the biosolids to go between like two rollers that would squeeze out the water. And then centrifugation, where the biosolids are spun and the liquids and solids are allowed to separate even more. And then what comes out of all of this used to be called just sludge, and now it's called biosolids, because that's maybe a better marketing term for the product. So this is a diagram showing a generalized sludge processing schematic. You've got your solids flow, and what's important to recognize about this diagram, there's a lot of different processes shown here, but you also see this arrow kind of going right through. Every plant is different in how they process biosolids, and they can have some of these general processes or not. And then within those, they could have one or more of the boxes. So you might not have any preliminary operations. Maybe there is a storage tank, and then it goes into some sort of thickening. Sometimes this is a common one that you'll see is some maybe belt thickeners or centrifugation. Stabilization, this is the lime stabilization and digestion portion. Maybe some other conditioning. Maybe you still are adding lime or a polymer or common chemical additions. And then into the dewatering process, where you see centrifugation, belt filter presses, drying beds. Those are the most common. And then you might have heat drying or other processing, some more long-term storage. And then you might have some thermal reduction, maybe some incineration or something, and then to reuse or disposal. So every process is different. There's lots of options within each of these. But the basic process is we want to deal with pathogens, odors, and the water. And we're going to do that through at least stabilization and some combination of dewatering and thickening. This is a little diagram just showing in the United States approximately where all the biosolids winds up or how it's used. So about 28% goes to municipal solid waste landfill, 36% is reused in agriculture, 11% in Class A products. So this would be like a biosolids you could buy like in Newburgh, or a pelletized product that would go to like a hardware store that you could buy. Something that's not just biosolids straight into agriculture. Incineration, 15%. And then you've got like some forestry applications, construction fill, other. So one common use is in what they call minimum daily cover in a landfill, where you dump the municipal solid waste, and every day that has to be covered over. And And so biosolids are used as can be used as the daily cover. And I'm not sure in this diagram whether that's included in this landfill or in the other, but that's a common use. And then the last part is what is in biosolids. So I have here metals, nutrients, and other chemicals. Another big portion is just, it's mostly dead cells. It's mostly dead microbes that have come out of the process and then been stabilized. So there's a lot of biomass there that's not living anymore. So there's things like cellulose in it, but there's also, proteins and fats and things like that that are just stabilized. But also there's metals, nutrients, and other chemicals. So this is just taken from Newberg's website, where you can look at the composition of their compost that they sell in 2018. These are the nutrients, so different kinds of nitrogen, potassium, and phosphorus. These are things that we want. It can be used as fertilizer in our plants, but we want to be concerned about if there's too many nutrients when we apply, those could run off into waterways or seep into the groundwater and then cause problems downstream. So we want to apply only enough to fertilize and not too much. And then down here, metals is another thing that's regulated by the EPA. Limits for the metals and the biosolids, and then how much new grow compost contains. So metals and nutrients are the two most common that are regulated in terms of when we land apply, what we want to make sure we don't put too much into the environment. And then other chemicals. So more recently, in the last 10-20 years, we have been able to measure lots of little chemicals in biosolids a lot better. This is just a figure I grabbed from an article on the web that shows some of those kinds of chemicals. So nonylphenol and nonylphenol ethoxylates. These are potential endocrine disruptors. A lot of these are potential endocrine disruptors. PFCs are perfluorinated chemicals, PPCPs, pharmaceuticals, and personal care products. These are things that nonylphenol and nonylphenol ethoxylates typically come from detergents, right? These are surfactants. Triclocarban, triclosan are antimicrobials found in solid and liquid antibacterial soaps. And then down here, these are pharmaceuticals, ciprofloxacin and ofloxacin. So cipro, I think, common antibiotics that are used. So these can wind up in the biosolids. I did my graduate research, looked a lot at this chemical triclocarban, and in fact, one of the main chapters of my dissertation, a couple of them, were on when we land apply biosolids and then they get rained on, looking at in the surface water runoff and in the infiltration, how much of chemicals like these get mobilized into that, and is that maybe a risk to surface water or groundwater that we should regulate like we regulate metals or nutrients. Currently, the EPA does not regulate chemicals like these in biosolids. Some of these chemicals are regulated at a state level in the discharge from wastewater treatment facilities. Most are not in most states, and they're not in biosolids. Anyway, that's a little bit of a wrap up of what is in biosolids. Again, it's mostly dead cells. It's not, it's not raw sewage. It's been stabilized, but it does contain other things that we could be of concern to the environment. However, just to emphasize, a lot of these techniques, with the exception of the municipal solid waste landfill, when putting in agriculture, we can get a beneficial reuse of that product, right? We're using the nutrients in a place that we need nutrients. When we incinerate, if we have the right pollution controls in the incinerator and we are generating electricity from that incineration, that's a beneficial reuse of that product. And there can be beneficial reuse even at the treatment facility, for example, in the anaerobic digestion process, like I talked about. So biosolids are a place where we can recoup some of that lost energy that's wasted in our typical urban environment, in the same way that you might make like a compost pile to reuse some of your food waste from your house and reduce the amount of waste that's going out. Biosolids kind of serve a similar purpose, right? A way of reusing some of this lost energy from our system. And we're trying to get, out of landfills and into agriculture. But in certain areas like Oregon, for example, when it's wet for 4, 5, 6 months of the year, there's restrictions on applying biosolids during that period when the ground is all saturated, because it just is a high potential for nutrients and metals and things like that to leach out and run off into the waterways. So in Oregon, if you want to use for agriculture in the winter, what I've heard is that you need to transport or truck the biosolids over the Cascades into eastern Oregon where it's not as wet. And that's just really cost prohibitive because of the amount of energy it takes to truck them all over there. So there's a lot of policy things and just economics that goes into figuring out what to do with the biosolids. And Newburgh, for example, recoups some of that revenue through selling their biosolids to the public, but they don't nearly break even on their process. They lose a lot of money on it still. And in a time like right now where we're dealing with this pandemic and closing of non-essential businesses, their biosolids, they're not selling their biosolids to the public. So they're just building up, keeping them in piles around the facility, hoping that by summer they can start selling it. And this is really the prime time of the year when they start selling it, because people buy those biosolids and put them in their landscaping, in their gardens in the spring. So hopefully there will still be a market for them. I saw that they reduced the price from $13 or $14 a yard to $10 a yard for when they do reopen. So they're going to be trying to get rid of it. Anyway, so that's the lecture on wastewater solids handling. And be sure and take the quiz. The next topic will be on drinking water treatment.